Hello, everybody. Let me introduce myself. I am Joe Beda. I'm a principal engineer at VMware, and I'm here to talk about Kubernetes, which we abbreviate K8S because otherwise it'd be too long for my slide. The 8 is the number of letters between the K and the S. Decoder ring for those that are new to the Kubernetes world. Like I said, I'm a principal engineer at VMware. I was part of getting the Kubernetes project started at Google and started this startup called Heptio that we sold to VMware, a little over a year and a half ago. So let me jump right in. What is Kubernetes? And so for those who aren't super familiar, oftentimes we'll see Kubernetes described as a container orchestrator. And I think, that's a decent name. I'm not a huge fan of it. I'll get to that in a little bit. But as an orchestrator, Kubernetes actually does a good job. And I think the idea here really comes into two things. You have a set of machines. You want to get the most out of those machines as possible. And this is really, if you look at the history of Kubernetes, what happened, the previous systems at Google, things like Borg. The initial reason for doing those things was really to try and get as much out of your computers as you possibly could. But then something sort of strange happened along the way. In doing so, we ended up creating new APIs, we as an industry, that were higher level than just VMs or just raw machines. And I think that's really where things got interesting here. And so it went from being just an efficiency thing to being something that really created new abstractions, new ways of dealing with infrastructure for application teams. Now, like I said, Kubernetes is an orchestrator. The main job is to say, hey, I have a container or I have a container image. I want to run this container somewhere across a pool of machines. Make it happen. Do the magic. And that's really the core of what Kubernetes started as. But as soon as you start doing that, you start introducing new problems on top of that. Things like, how do I make these things talk to each other? How do I deal with storage? And so a lot of the things that Kubernetes brings in really are to deal with the dynamism of a containerized platform where different things are running in different places at different times. All right, so what is Kubernetes really? Well, at its core, Kubernetes is a database. I bet you weren't expecting me to say that. So it really is essentially a way to store desired state. What do users or other parts of the system want to have happen? And then reflect status. What is actually happening in the world? And if you look at the Kubernetes API, what you'll find is that every single object has spec and status. Spec is what does the user want to have happen? Status is what's really happening. And then Kubernetes takes that database, wraps it with some policy, authentication, authorization, all sorts of other sort of policies, schema translation, that type of things, and then presents an API to the world. And so that database really is the core of Kubernetes. All of the sort of containerness, all the container orchestration actually happens outside of that sort of core of Kubernetes. So here's a beautiful block diagram that I created to represent this. And what you can see here is that etcd is the database. This is a certain class of databases that also traces its way back to some stuff that was done at Google, that this server called Chubby, horrible name, that also influenced and inspired things like Zookeeper. The API server is the only thing that should be talking to etcd, and then everything else calls into the API server. And what's interesting here, and what I want everybody to notice, is that whether you're a user, a human, my stick figure up there, or whether you're other pieces of code, everybody goes through the API server in that same structured way. And then what we have here is that we have the scheduler. That's a piece of code that actually decides which container is going to run on which node. And then we have the controller manager, which does higher order things like, I want to run 10 copies of this, or I want to use this particular upgrade strategy as I'm moving from A to B in terms of versioning. And then similarly, the actual nodes themselves, that are running Docker or some sort of, descendant of Docker using this interface called the container runtime interface. Those things are adapted to Kubernetes with this daemon on the node, this agent called the kubelet. And that's another Googleism, Kubernetes kubelet, Borg had the Borglet. There was another system at Google called Omega that had the omelet. The joke always gets a laugh. It's hard to tell if you're laughing with the virtual format. So I'm just gonna assume that you are. So the core thing here is a controller. So a controller is, you know, and this is similar to your thermostat in your house, right? You set a temperature, I want it to be 68 degrees. And then the thermostat then says, okay, air conditioner, furnace, do what you need to do to be able to do this. It actually tries to actually run those things to be able to make a desired result, 68 degrees, happen using the systems that it has. Similar thing with an oven. You want your oven to heat up to 350 degrees Fahrenheit. That's something that, you know, the oven automatically turns the heating elements on and off to make that happen. We want Kubernetes to be similar to that. I want to have 10 of these types of containers running. Okay, there's going to be a controller that tries to make that happen. And if there's too many controllers, too many containers, it's going to delete some or shut some down. If there's not enough, it's going to start some more up. So the whole idea of a controller is to make relentless forward progress. The idea is you take this desired state, you then do whatever you need to try and take some steps, one foot in foot in front of the other to try and actually work towards that desired state. This here is a picture of me and the family from a couple of years ago. We had just hiked out of the Grand Canyon. And so, you know, we'd spent 4 days getting down to the bottom of the Grand Canyon and then working our way back up. And you know, and if you've ever gone hiking with kids, you know that like it's not easy, right? Especially when you're getting out of the Grand Canyon. But like it really reminds me of what you want controllers to do. You know, the desired state for us at that time was being at the top eating ice cream. The reality is that we weren't. And so we needed to, you know, at one step in front of the other, get ourselves out of the Grand Canyon. And there may be intermediate states along the way that, you know, your desire is to be out, but maybe you have to camp overnight. Or maybe, you know, hey, part of the trail is closed and you have to take a detour. Those are things that are going to be unexpected. And you want to make sure that the intent for what users want to do is flexible and durable enough so that it can withstand unexpected situations like that. So in Kubernetes terms, if you are running 10 pods and let's say a machine disappears off the network, and now all of a sudden you're running 9 pods or 9 copies of a container, you want the system to say, oh, let me self-heal. The goal is 10 of these things. Let me go ahead and create 10 of these things. And then that actually is a way for Kubernetes to sort of create that self-healing based on desired state. When we looked at that diagram earlier, one of the things you might have noticed is that all of the arrows pointed into the API server. The API server really shouldn't be calling out to any of the other components, and the components themselves shouldn't actually be talking to each other directly. Now, there's some few practical exceptions in Kubernetes if you dig in deep, but that sort of rigor around everything goes through the API server is pretty well implemented across the system. Now, what we have here is a sequence diagram of how this actually works. What we find is that a user will go through and create a pod, write to the API server, and then the API server will then write to etcd and then return. Meanwhile, the scheduler will notice that, hey, there's a pod that's been created, and for all intents and purposes, pod and container here are equivalent. So let's not get into too much detail right now on that. The scheduler will notice that there's a new pod. It hasn't been assigned to a node. It'll then go through, assign it to a node, write that binding back through etcd, back through the API server that then writes it to etcd. And then finally, the kubelet will notice, hey, there's a new pod that's been assigned to my node. Let me go ahead and do what I need to do to get that pod running. The desired state for the kubelet is that this pod, this container should be running on this node. The kubelet may actually say, oh, I don't have the image bits downloaded. Let me go ahead and actually download the image bits for that container so that I can run it. And so it essentially, you know, does things like call Docker run or the sort of API equivalent with the newer interfaces that we have. And then it'll reflect the status back through the API server and then into etcd. And so what you'll find is that these things don't actually talk directly to each other, but essentially leave breadcrumbs for each other by writing data into etcd and then having controllers notice when something changed. There's special mechanisms in etcd in the API server to reflect changes quickly so that they can actually go through and react to that. And we find that this is a very, very stable distributed systems programming model, because what we find is that if something bad happens, if something crashes, if a notification gets lost, it's very easy to say, hey, just look at what's in the database and then react to that. And the rest of the system should be able to converge and self-heal regardless of what happened in the meantime. I think if you compare this to, a system like a Kafka with events, so we call this level triggered versus something like Kafka, which most of the ways that people use that would be what I would call edge triggered. If you lose one of those events, or if you get it delivered twice, bad things can happen if you're not careful. And it actually sort of, losing an event is an impactful thing. And so that's one way where, when I look at Kafka, I'm like, oh, it's a database with some queuing mechanisms built on top of it. Whereas here, it doesn't matter how you got to that desired state, as long as you're dealing with it, the intermediate states don't matter. And so that's what we mean when we say that Kubernetes is level triggered. So when you add all this together, this is why I don't like the term orchestration, because orchestration implies that there's a plan, that there's a score, that there's a conductor, and everything is actually pre-planned from the get-go. And in reality, this is more like, this is more like jazz improv. So if you're in an orchestra performance and something unexpected happens, like, a car alarm goes off and there's no sound insulation, that'll be pretty disruptive to the performance, right? Because that car alarm was not in the score. It wasn't part of the plan. Whereas with jazz improv, if you hear a car alarm, it's just as likely that the players will actually work that into the music, because they're reacting with each other, they're reacting with the reality, they're reacting to the vibe of the room, and in doing so, they're creating something sort of, generative based on the reality on the ground. And that's what we want in distributed systems. If a node fails, we want the system to actually be able to deal with it. If there's an unexpected load spike and you have an autoscaler kick in, we want the system to be able to deal with it in an intelligent way. And I think jazz improv really is the analogy there that works for me. All right, so that's sort of the core of how Kubernetes works. Now, when we start looking at those controllers, I'm going to go into some detail here. They're really layered on top of each other. The goal out of Kubernetes when we were creating it was to create a little bit of a sort of a Unix philosophy type of thing. A bunch of primitives that can be used with each other and layered on top of each other to be able to produce a result. And for me, I think the mark of a durable platform over time is when people can use the thing in unexpected ways. If you build something and then somebody uses it in a way that you never actually even thought about or considered, that is the mark of a successful platform. And that's something that's personally very exciting for me. And so layering these primitives, these composable systems, infrastructure Lego blocks, that I think is the heart of what makes cloud from an application person's point of view. That's what makes Kubernetes successful in terms of being able to extend it and take it into directions that we never actually thought about when we were creating it. So let's get down to some specifics. At the core, with respect to containers, we have the pod. And I said, view this kind of like a container. The reality of what a pod is it's a footprint on a machine. It's resources on whether a VM or a physical machine. It's essentially a resource reservation on that machine. And in that resource reservation, you want to do configuration, run a set of containers, have them be able to talk amongst themselves in certain ways, allocate networking resources and attach those things. From a storage point of view, oftentimes you'll specify, hey, I want to have this network attached storage be automatically attached and surfaced into this pod, or I want to be able to allocate local disk space in a certain way to this pod. And so the resource allocation is what we call a pod, and that's really a primitive in the system. Building on top of that, we have a replica set. And so a replica set takes a single pod. It actually takes a template, essentially a blueprint for a pod, and it takes a number of replicas, and it wakes up, and this is that controller again, and says, hey, I went 10 pods, I have 0, let me start up some pods. or it wakes up and says, I don't know what the heck happened. I now have 15 pods. I want to have 10 pods. Let me go ahead and kill some. And so that's how the replica set works. And so it doesn't matter how things changed or what the intermediate states were. All the replica set does is say, here's how many I should be having. Here's how many I currently have. Let me make some relentless forward progress to try and make my desired state match reality, or reality match my desired state, rather. And then we layer on top of that another object that we call deployment. Replica set doesn't know about versions, deployment does. And so the idea is that if you're doing a configuration change, deployment knows how to actually manage multiple replica sets to be able to actually take one replica set away or create a new replica set for the new version, dial up the number of replicas in that one while it dials down the number of replicas in the previous one. There's another thing built on top of pods, and I don't have slides for this thing called Stateful Set, which is really built to deal with the idea of that, hey, these pods are not totally fungible. There is actually, you may want to have shards or assignments or things that deal with them. And so you want to deal with them in a much more structured way. And so it reuses the pod primitive there, but it actually uses it in a new way by building on top of it, having a more structured way of dealing with it. And that's what a stateful set is. And so what we'll find is that a lot of folks, as they're dealing with databases and running stateful systems on top of Kubernetes, that stateful set reuses the Kubernetes primitives in a new way. Now, this is all fine and good, but one of the things that we discovered as Kubernetes started seeing some success was that everybody was excited to create new controllers, new objects in Kubernetes. And so if we think about Kubernetes, like I said, at its core as a database, the different types of objects, whether they be pods, stateful sets, replica sets, deployments, you can kind of think of those things as being sort of tables in that database that is the core of Kubernetes, and with their own schema and such. Initially, the set of tables that were built into Kubernetes was fixed and built into the core. And then Brendan Burns, one of the fellow co-founders of Kubernetes, started experimenting with what eventually became what we call custom resource definitions. And you can think about this as essentially creating custom schemas, custom tables in that database that is Kubernetes. And along the way, you inherit all of the API machinery that Kubernetes has to be able to, do ACLing, access management, rate limiting, tenancy, all that stuff sort of comes along for the ride as you're actually using Kubernetes. And then you get essentially a uniform tool set for dealing with both things that are pre-existing in the system and new things that people can add and extend the system with. And so I mentioned deployment earlier. It does essentially a rolling deployment. Kubernetes doesn't have a built-in way to do a blue-green deployment. But it's easy to take and extend Kubernetes with a custom resource definition so that you could create a new blue-green deployment object, which is a peer to the built-in deployment object by combining a custom resource definition and then your own custom controller that breathes life into the dumb data that is that custom resource. And so one of the interesting things that we see come with this is what we call the Kubernetes resource model, which is essentially the standard sort of schema shape of a Kubernetes object. These are things like metadata. How do we name these things? How do we actually deal with identifying and getting a unique key for these things? Generally, every single object in the Kubernetes world has a spec and a status. The spec is the desired state. The status is the real state. There's a bunch of other metadata around sort of annotations and labels that let you do grouping across a bunch of things. All those things are part of this Kubernetes resource model. And so when folks start using CRDs, it's not just an anything goes type of schema. They really, get the most by lining up with the opinionated way that Kubernetes stores resources that lends itself to being able to write these controllers that can add new behavior to it. So this brings me to operators. And this is where I think things really start to get exciting. Traditionally, we think of operators as people, just like computers, our people used to be people too at one point. But it was the Core OS folks before they were bought by Red Hat that coined the term operator. And, I think people will argue with the definitions. For my mind, the definition of operator is a domain-specific controller that knows something about the workload that it's actually controlling. And so what we find is that operators are a way to build on top of everything that I talked about here around desired state and bring that into the application, or at least the service domain. And so one example would be like, how can we take sort of a database system like Postgres or MySQL and then start adapting that to Kubernetes? Well, you could build an operator to do that. Take all of the run book, all the sort of like institutional knowledge for what it takes to run a database, start to distill that down into code, build that as a way that actually sort of adapts those things into Kubernetes. So that way, if a node fails, if something unexpected happens, that operator will run its control loop and actually try and heal the system so that it'll automatically say establish quorum, or switch over a primary and a replica of a database as you see unexpected things happen. And we're starting to see this. There's this explosion in the cloud native world around operators to be able to adapt them to this super dynamic system that Kubernetes is. Because Kubernetes is all about dynamism, make things come and go, deal with the reality, deal with unexpected situations. Databases generally don't like dynamism, at least traditional databases don't. If something fails, it's generally an exceptional thing where you want to, usually, traditionally, humans have to intervene to be able to fix it up. We want to reduce and remove that human factor and make systems self-healing, whether those things be existing database systems that are being adapted to the dynamic world of Kubernetes, or provide the right primitives for newer databases. Again, this conference, Distributed SQL, right, is really about creating new databases, new systems that can then work with Kubernetes to be able to deal with this. Right now, we kind of view operators as something that sits outside the database. I imagine that over time, we're going to start seeing databases that automatically build that operator functionality into the database so that they assume, or at least they are built to run on the dynamic systems that you get with things like Kubernetes. All right, but it's not all roses. Writing controllers is still kind of a pain. I think there's a whole bunch of different ways to do it. None of them are perfect. I think we're still figuring out the sweet spot and the patterns here. It's still early days in terms of writing controllers and operators. What I can say though is that people are experimenting, and I think this is part of the excitement across this ecosystem, is that there's a ton of innovation, there's a ton of passion that people are bringing, and we're starting to see new ideas emerge. One project that is not super active right now was this thing called Meta Controller, which was a way to sort of take a sort of serverless webhooky point of view towards writing a controller where there's common patterns, and you can sort of write, a blue-green deployment controller, because again, not built in, you can write one of those things in something like 125 lines of JavaScript. There's other systems where folks are like, okay, what if you're not a programmer, but you want to write a controller? When we think about operators, their language are things like Bash, right? They can hack together some awesome Bash scripts that'll really accelerate what they do. Is there a way to take those Bash scripts and actually start bringing them into Kubernetes or similar types of sort of automation to start bridging the gap between the world that we're in and the world that we want to get to? And so there's other systems that are emerging that are really targeted at a less programmer audience for starting to build up these controllers. And then, and then looking beyond Kubernetes, there's really a whole bunch of complementary technologies that are really coming into play. And so, we got blurry there for a second. Kubernetes itself is evolving. What we find is that the underlying storage systems, initially all this stuff was built in, but just like we have extensibility for controllers, just like we have extensibilities for the runtimes, it's not always Docker anymore. It could be this system called Cryo or Container D. We also have extensibility for the storage interfaces. And so this is a container storage interface, which is a way to extend Kubernetes such that Kubernetes says, give me a volume, and here's the parameters of that volume. And then it's essentially a driver model to provide that volume via some mechanism. And folks are doing some really, really interesting things about, hey, we can do, network attack storage, things like EBS volumes. You can adapt this with NFS. Folks are doing some other things that have more sort of client-side caching and sort of a git-like commit things with deduplication. Super interesting stuff like that. There's also been a lot of work with being able to use local disk access in a much better way. And so if you have a local volume, you know, say an NVMe volume on a Kubernetes node, you can start taking advantage of that and do that in a structured way such that, hey, you know, that's securely being surfaced to a single user. And you can allocate that over time and make sure that if something gets stopped and restarted, it can reattach to the data that it had before. Really cool stuff going on there. All sorts of things to work with the system, things like taints and tolerations to make sure that you don't have two things running on the same physical node that you don't want to be running there, or you need them to be running on the same physical node or in the same rack. Pod disruption budgets, making sure that you don't churn users, applications and systems that fast. All sorts of really interesting stuff going on there. And then other systems outside of Kubernetes. Identity, how do we create secure ways for systems to talk to each other, even across cluster? Very important for things like distributed databases. Coordinating across clusters themselves, very active area where there's a lot going on. How do you advertise, you know, that a service is available and provision it? You may implement your service on one cluster, or it may be something that's not even implemented on Kubernetes itself, and you want to actually advertise that into Kubernetes. We're seeing that sort of operator controller thing start to be a way to interface to cloud provider APIs. And so these are being provided by the cloud providers themselves, but also there's open source projects that are starting to surface this stuff also. So a lot of really interesting stuff going on around that core and around extensibility to really adapt Kubernetes to stateful workloads and more complex workloads. So this meme just hit a little while ago, and I think it's hilarious. What we see in the background here, you know, in front of the, you know, crazy conspiracy theory is the CNCF landscape. What this says to me is that there's a heck of a lot going on here. It's very confusing to users. And to some degree, this is the early state that we're in with respect to Kubernetes and the cloud native ecosystem as a whole. This really, to me, says that there's a ton of innovation going on, but it's still very hard for users to wrap their heads around it and make use of it. And I think we're going to see that shaking out over the next couple of years. And I think it also shows that we're still, you know, relatively early on this journey. Something like the diversity and the sort of chaos that we see represented here is almost inevitable, because either you're going to see something highly curated, which requires gatekeeping, or you're going to see something that is chaotic and lets anybody come and participate. And I'd much rather have the second rather than the first. And that's something that really excites me about Kubernetes and about this entire ecosystem. And sort of those control systems, I think, you know, I've been talking about those in terms of like, you know, dealing with stateful systems and databases. But I think, you know, as we look towards the future, we're going to start seeing people start to use these level triggered systems, these controllers, to start controlling more than just software systems. For me, it really, you know, Kubernetes starts to become, you know, what I'll call a distributed systems kernel for making it easy to take these well understood patterns and apply those to all sorts of other domains, not just about starting containers up. And that's what keeps me excited. Kubernetes is about 6 years old now. It's kind of entering a certain type of middle age. This is what I think the future holds and what really keeps me excited. So thank you so much for letting me talk and listen to me ramble at you. Hopefully the rest of the conference is great and everybody gets a lot out of it. Thank you so much.